the system. So this acceptance test procedure is you as the hospital, and maybe just say something that I usually say at when I give talks at like a PT cog or such, and usually I say this to kind of upset the vendors purposely, is uh the vendor, whoever the vendor is, whether it's a variant that has, 1,000, 10,000 linear accelerators or some proton machines, or whether it's a new vendor that has one proton machine. Uh, for the most part, they've never actually treated a patient. They might show things that say our equipment has been used to treat 10,000 patients, but they themselves, mostly the ones that designed it, the ones that are engineering, the ones that are selling you the machines, etc., they've never actually treated a patient. So as far as the radiation oncologists, I know we have a couple in the audience, they've never actually met with the patients, had to contour their tumors, or a physicist actually be the one responsible making sure that beam is being delivered properly. So just saying that again, because a vendor may say this is our acceptance test. So that this is how we want you to test the performance of the specifications that we have, uh, and how it operates with the other systems you may have. But they would always want to, they being the vendors, and nothing bad about the vendors, but they want this acceptance test procedure to be as meaningless as possible, because that's where they get paid. They want to say, look, this is my spot size, do this type of measurement, and it will show that it's good, and then write me the check for the whatever 30 million, 20 million, 50 million, whatever it is you're buying the system at. But I really think it's the responsibility of the hospital, and therefore the medical physicists and the physicians, to make sure they're actually accepting a machine that they're going to actually treat patients with, and that it is performing as well as they expect it to perform. Saying all that because these are the tools that you have to do these type of tests. And later we talk about some of the things that deal with contracts and stuff, but I want that to be really, really clear. I'm not saying that the vendors are being, not straightforward, but it's in their best interest to make these kind of tests as simple as possible so they can pass and get paid. But you're responsible for treating the patient. You want to make sure the machine is performing as good as it can possibly perform. And not just on one day, but, over the extended lifetime of the machine. This is a screen capture of different things that we test. So we already talked about radiation protection and survey. Something else that the regulators would be interested in, maybe not the radiation regulators, but there's many different types of regulators. They'll be interested in the safety and system interlocks. For example, if I try to walk in here, it should turn off the beam because I shouldn't be in there, these kind of things. And also of the actual radiation going to the patient, that the machine can actually turn itself off if something was going wrong, or these kind of things. Same thing on your regular linear accelerator. If there's some type of collision, does it properly stop? All these kind of things. Those are some of the regular safety things and aren't necessarily radiation specific. But, knowing how those operate. Then you have the things that are going to be your mechanical and alignment. So again, you've seen pictures. These are really large devices, and we're trying to be very precise down to like millimeter level. So how we test these different things, the mechanical rigidity, and there's also not just the beam delivery cells, the gantry rotating around, the patient positioning system. All these things have to work together. And then there's actually then the dosimetry and the pencil beam scanning itself. How do you actually characterize these different things? Spot profiles, the depth doses that they do, etc. How well does the system itself perform, not just on one day, minute to minute, but also day to day, week to week. So during this acceptance test procedure, from the very start to the very end, there you should have some information there of how well the thing is able to reproduce itself, not only in like dose rates and such, but the monitors themselves, how do they perform over time? Regular stability things, different things we'll go into. And then something that's uh, also very important that isn't particular to proton therapy, that is general, is then all the various imaging thing. Are you going to have combing? Are you going to have fluoroscopic, KV imaging? All these different things. You still need to make sure those are tested properly. They're working well. Because if you're and those that in the clinic, no, if your imaging isn't very good, then your therapy isn't going to be very good, right? Because you can't actually line up the patient properly, etc. And then how this system actually integrates with everything else, you record and verify, uh, how it transfers to your hospital systems and stuff like that, how that's going to work. And then things about the efficiency, not only on the treating the patients, but as on the medical physics side, again, there's a lot of QA, quality assurance, and quality controls you have to do. And the more efficient that uh, physics can do these things, and just being selfish, the easier we can make it on ourselves. It's not necessarily about making it easy, and that way the we don't have to come in at midnight and do all kinds of measurements. But anytime we physics is having to do some type of quality assurance, some type of quality control, that means the patient is not being treated because we're using the beam to do these measurements. And again, the point of setting these up, of doing the radiation therapy, so we can treat the patient and cure their cancer. And we want to make sure that they are getting the proper treatment, but knowing that every time we're there taking measurements, that means the patient isn't being treated. So is the system set up so that could be as efficient as possible, so we can, again, treat as many patients as possible? Okay, so that's things to kind of think about going through. And again, this is the acceptance and commissioning and quality assurance discussions. That's why that part's there. Let me move this. There. Okay. Okay, so components of a particle system commissioning. Again, commissioning, and for those that these words might mean different depending on which field you're in. When we say the commissioning, so there's one part where the vendor is doing commissioning. That means they're getting their equipment up to the level that it could be used clinically, right? So making sure the radiation working, they got to do all kinds of tests, getting it ready. And then so there's that kind of technical commissioning that the vendor does. And then there's the acceptance test. That's where we go and test all these things that the vendor says is supposed to work a certain way, and we're checking, making sure it's actually working that way, so we are sure that they're delivering what was promised. And that's the acceptance test. And then there's the clinical commissioning. So the technical commissioning that the vendor is doing, making sure it's operating on that specification, is different than the things we need for the clinical portion. So there's data, there's information we need on the clinical commissioning so that we could treat a patient effectively and put into the treatment planning system and these other things that aren't necessarily part of the technical commissioning. So there's all these three phases, and we need equipment to be able to do this. We can't just show up and look at it and say, oh, it looks good, right? We need tools to be able to do this properly. And during the technical commissioning portion, this is part of it when you're also talking with the vendor and such. There's certain tools that they may need only one time, but you need a lot. So maybe you are the hospital is the one buying that particular system, and the vendor will use it for a month or two, and then you're going to use it the next 20 years kind of thing, or vice versa. There's something you only need maybe one time during the acceptance that you don't necessarily want to go purchase this thing for whatever it is. You're only going to use it one time during acceptance. So maybe it's something the vendor has, and you negotiate that you're going to use their tool in a certain way to do the test. So just things to kind of think about. So the system performance testing, just beyond the regular acceptance testing, development of the planning delivery clinical workflow. So you got to have this kind of laid out. So when you're doing your acceptance testing, the components are working together. not going to spend too much time on it. I was talked earlier about the dual energy CT scanners, but how is your CT scanning commissioning? So we need to talk about that because these are also tools that you're going to use, and if you're going to do single energy or dual energy and what that means and how that interfaces with your system. If you're doing a dual energy CT in a certain way, does that system that you have, that vendor, can they actually accept it so they could do a cone beam and registration, etc.? Knowing what your quality control and QA procedures could be daily, weekly, monthly, so you can do proper tests during acceptance and commissioning so that your regular quality assurance is as meaningful as possible. Then a lot of this data needs to go into whatever trim and planning system you're getting, and that's a different vendor, and knowing how that's going to work together. And then, of course, the training the people. So this is during the time during the acceptance test and your clinical commissioning, and to some extent during that technical commissioning, that's when you're also getting your training. The therapists are learning how do you operate this equipment, how to operate the robotic patient positioning, how the physicists are learning how the monitor chamber is going to work so they can do the quality assurance, all these different things, how the image guidance is going to work. During this time, is when you're also doing that training. So having that in the forethought to know when you're going to do training, when you're actually going to be doing measurements, and all that has to be kind of thought of so you can, again, it's about being efficient so you could get to being able to treat patients quickly and effectively. So I showed this picture before, but when you're doing before you buy any tools, you kind of need to know how your system is going to work so you know which tools are the right tools that you need to use. In your as you for the hospital, you're really not going to do any measurements over here, right? You're not going to be back in the beam or anything. Everything you're going to do is going to be in the treatment room. So you don't need to worry about beam monitors back here or these kind of things, but you need to know how those are going to work and how it's going to influence what you're going to measure in the treatment room. This is a beam nozzle. All nozzles are a little bit different, but there's different components in here. And knowing how those components are together so that, again, when you're doing a measurement, when you're doing a spot size measurement, you can know what influence changes back here in the synchrotron are going to make to your measurement. This becomes important because there's always going to be a downtime. There's always something's going to happen. The machine is going to go down. The vendor is going to come in and do things to it. And honestly, you're not really going to know what they did. They're going to go in and kind of kick it, do something to it. And also, going to start working. And then you're going to be like, what do I need to test? Because I'm not exactly sure what they just did. What do I need to test to make sure that this is still operational? And the more you know the system, the more you understand what they did so you can do more effective tests. And if you don't really understand that part, and I'm not saying that you have to understand all those parts, then you have to do more things because you have to ensure that now when the patient gets on the table to get their treatment, it's going to be highly effective. So you have to do more things. Again, it takes more time. So it's just kind of that back and forth of the more you know about the system, the better you can do the test to make sure the patient treatments are very effective. Knowing how the scanning is going to work, how does the system actually do their scanning mechanism? There's different ways you can approach scanning, continuous scanning, discrete spot scanning. There's different ways you could do continuous scanning. How the thing is going to change energies, whether if you have a synchrotron or a cyclotron, multi-energy extraction, single energy extraction. You need to know those things because then you need to know how the equipment you're going to buy, which we will talk about in a bit, how it's going to respond in these different scenarios. And also the dynamic range. So at the end of the day, when you're doing these tests, what you're really testing in the nozzle, there's dose monitors and spot position monitors, things to make sure that the vendor has to make sure the system is operating correctly. And what you're really testing is to make sure those are operating right. Because if those are operating correctly, if something goes wrong, there's going to throw a beam abort. If the beam is going to the wrong place, the system should prevent that from happening. At the end, anything it should detect is not going to the right place and stop. So you have to have equipment that is able to properly test those things and know how to test those, what we call interlocks, to make sure that that system will actually stop if something was to go wrong. Okay. So the first thing when you're doing these commissioning, you need to precisely characterize the spot properties, such as the profile. The main things are the profile and the depth dose. Here we call it the integrated depth dose for now. So here's the integrated depth dose. What this is a measurement of saying how much radiation is being delivered for a particular energy through the depth of, here in this case, a water phantom. And during that time that you're doing those measurements, the beam itself is getting bigger and bigger. Here's a quick expression that doesn't get everything, but gets 90% of it, of how the beam is going to be spreading as it's interacting. So what does that look like? So here's a kind of cartoon showing that it's going to be somewhat of a Gaussian shape. And it's important to know what that beam comes out like, because though everybody talks about, and you go to different things, they'll talk about the beam being a Gaussian shape and such. It doesn't have to be a Gaussian shape when it comes out. It could be different. And you have to kind of understand that. And the reason for that is when you're doing these depth dose, you have no other mechanism to really understand what the beam is doing except for taking these measurements, because you don't know the characteristics of the beam coming in. If you knew everything about the beam coming in, kind of like when you're doing a high energy physics experiment and it's something called like the phase space that's coming out, and you know that very well, then you could do the calculation of what's going to happen in this water phantom. But you don't know what's coming out of that machine 100%. So you have to do these measurements to kind of infer what's coming out. And part of that is what that beam actually is shaped like. As some of you may know, when you're doing these beam optics, so all these magnets, we call them beam optics. And I kind of mentioned that before. There's dipoles and quadrupoles to focus. You could change those optics so that the beam does something different. You could do it so that they're focused at isocenter, or you could do it that they're not focused at isocenter, that they're diverging. And that'll give different beam characteristics. And you don't necessarily know that up front as you in the clinical side. So you have to do these measurements to check and see what's actually happening. And what this is just kind of showing is that the beam usually starts out small. And once you're going in through here and through water, it's going to get bigger and bigger as it goes through and as it's delivering its energy. So this is kind of showing what energy deposition depth and what the beam size is actually happening. So why is this important? You need to know this because these are the things that go into the treatment planning system. So then treatment planning system can do these calculations properly to predict what the radiation is going to look like in the patient. Okay, so you need to do these. And the reason I'm showing this is not to see the math or what's happening here, because these are actually just approximation of what's actually happening. The main thing is here's one set as it's coming through in air versus in the water. If you have range shifters or different things, you have to do these kind of measurements. And though we're treating the patient, and when we treat the patient, we treat them, obviously we're treating the tumor in their body, so there's already the scatter. One thing that's important, and one of the key acceptance tests that you'll be doing is doing the in-air spot profiles. What this means is, what does the spot look like when it's not interacting with the patient? It's kind of as pure as it can be, so kind of in air. And you have to take these measurements at different points. And there's different tools that you could use, and we'll talk about the tools in a bit. But this is things that are going to start characterizing the beam and what's coming out of the machine at every single energy. Because again, the machine can produce many energies. If it's a synchrotron, it's probably going to produce somewhere about 100 energies. So every couple millimeters, you'll have another energy come out. If it's a cyclotron with a degrader, that could be even finer steps. So you do as many of these measurements to get a good understanding, not exhaustive, but a good understanding of how those beam characters are happening. And anything that goes in the beam, you have range shifters, you have things called ridge filters, different things interact with the beam. Okay, so now how do you actually do this? How do you measure these spot profiles? So the first thing is you're system can scan the beam at a certain what we call field size. Now, for instance, I work a lot with the Hitachi system. The Hitachi system has a 30 by 40 field size. Uh, the traditional photon systems, they have a 40 by 40. So most people are used to being able to treat patients 40 by 40, and this is centimeters. So you could treat a good sized field. Some proton systems have field sizes that are like 20 by 20, 20 cm by 20 cm. So if you're used to things being 40 by 40, and now you can only do something 20 by 20, well, there's some things you can't. Maybe you're used to doing whole breast treatments that does the lymph nodes and everything. You can't do that in a 20 by 20. So then you have to do these complicated things called patch fields. Okay, that's the difference. That's the field size. But when you're measuring these things, you have to know what field size you have so you can measure the different points. Because the beam, as it comes down the center axis, depending again how the system is designed, when they go off to the corner, whether it's 20 by 20 or 30 by 40, whatever field size is, that beam has a little bit different characteristics. And if the system isn't well designed, and again, there are some systems that are not very well designed, the beam at the center is going to look great. The beam off to the corner is not going to look so well. It's going to get skewed. And depending how skewed it is, maybe you can account for that in treatment planning system, maybe you can't. So maybe they say they have a 25 by 25 field size, but the beam is so skewed out here in the corner, it's not usable. So then the usable thing is 22 by 22. Saying those numbers because those are a particular vendor in one of their particular systems. That's what they said, that 25 by 25, but nobody can use it. They can only use 22 by 22 because the beam just looks so weird out there. You can't actually model it right. And if you try to use it in a patient, you're not going to do the calculation right. So understanding that aspect is very important. But now if you're going to do this, you have to be able to have a tool that you could do this fairly quickly. So have a large area and high resolution because you want the resolution. Again, when we talk about modern systems, when we're talking about in-air at a high energy, the sigma. So if we assume again that it's basically Gaussian, the sigma is going to be maybe 2 millimeters. So full width, half max of maybe 4.5 or so. So you need things that are, at least a millimeter, if not more resolution to see if the beam actually looks the way it's supposed to. So the potential detectors that are out there, these are, there's different ones from different vendors. There's one called MyQA Phoenix, and I'll show what it looks like. Oh, I just did now. So this is that one. So this is a particular system. I'll talk about this and other ones similar a little bit more in a bit. But you're able to measure profiles. There you go. You want to also ensure that the spot intensity, so that's when we talked about dynamic range. If you try to measure a profile, but the detector you have doesn't actually meet the dynamic range of the spot coming out, because remember, it's going to be Gaussian shape. So it's going to be high in the core, maybe low out here. For this first one, maybe you just need the first order approximation, so just the regular Gaussian. Well, can you actually measure that? Does that detector you have that dynamic range? And also, does it have the dynamic range depending on the dose you're delivering? Some systems, depending how much dose you're actually delivering, whether it's going to call a heavy spot, let's say something that's going to have 10 to the 8th protons in it, or a light spot, something that has maybe only 10 to the 6th protons. So that's an order of magnitude, 2 orders of magnitude difference at the core versus at the tail. Does the detector you have, can it do also that dynamic range? Because the spot characteristics when you're doing a large heavyweight spot may be different than when you're doing this smaller lightweight spot. So again, having that difference and one knowing that there is a difference, that your system will operate differently under those two characteristics than knowing if your detector can actually measure based on those kind of characteristics. Here's another one for just like a QA. This is also measured by the Phoenix. What this helps with is when you're actually now doing a certain pattern. So the machine is actually now delivering a certain pattern. Well, how effectively is it delivering that pattern? So you could do these. So this this particular system, the one shown within the Phoenix, have different things inside of it. So you could deliver and check the edges and such. So, and it has some analysis. And what this does, it helps you understand really the characteristics, not only on the central axis, but off axis, and also at different dynamic ranges, and also reproducibility. So it's something that you can measure today and then measure next week and make sure that the beam is actually keeping its characteristics the same. Here's a different one. This is a logo system, and this right here is called the links. These are just names that different vendors give these equipment. So these are all scintillator devices. And so, the way scintillators work, you kind of hit them with the radiation, it kind of lights up. You have a camera that looks at it. The vendor that you get these equipment from should be able to give you the specifications, but you have to make sure that it's not being skewed, right? So, if you hit the light and anytime you have a camera that's looking with the mirror bending it so you can look at it, you're going to get some distortion on there. Now, usually the vendor would already go back and try to correct this distortion, but maybe not right. So you got to make sure if what you're seeing, is it actually a detector issue or is it a beam issue? So now sometimes not only do you have to worry about the beam, you have to worry about the detector you have itself. Is that actually performing properly? So there's always complications no matter what you're looking at here. But these are different systems. The other thing is with your equipment vendor is, can you actually mount anything to that nozzle? So this is a gantry, and the gantry is going to rotate depending what you do. Maybe they rotate all the way around 360. Maybe it's a half gantry, whatever it is. Well, when the gantry is rotating, those magnets are rotating, and when the magnets rotate, it changes the phase space coming in because the accelerator is always in one plane, right? So it's always in this plane, and it comes in, and now it's going to go in a new plane. Oh, and when you start rotating, it's a different plane. So the beam has certain characteristic. It has a certain physical shape and a shape in momentum or in phase space. And when you start changing the orientation, these things change. So what looks like at 0 degrees and at 90 and at 180 could be very different. Again, depending how the equipment vendor has set up their system, if they actually calibrate everything properly. So it's important to be able to take these measurements at different angles. And then it becomes relatively painful if you can't mount this on your gantry. So with your equipment vendor, can you actually mount things on there or not, or different things? So something to take into account. So that's just talking about basic spot size. Started with that one because it leads into this, the IDD. An IDD means integrated depth dose. So this is the one time, this is maybe the only measurement you're going to do where you're actually, for a spot coming in water, that you're going to try to measure what it looks like in depth. And what you want to be able to do is gather everything, be able to measure for this case, all the protons that are coming through at different depths. So you need a large detector for that. So you need a large active area, usually a parallel plate type chamber, and I'll show why in a bit. And you usually have to do this in a water phantom. The water phantom, because standard we do measurements in water. And the reason you want liquid water as opposed to maybe some plastic or anything is because you're actually going to be moving this to take measurements at different points along this curve to be able to ensure the characteristics of the beam as described is what you're actually measuring. There's different chambers that you can use. There's these are manufacturers, PTW. They make a Bragg Peak, has a Bragg Peak chamber. They call it the Bragg Peak 150. It has a 15 centimeter diameter. The PTW Bragg Peak, their standard one, has a sensitive volume about 8 cm diameter. IBA has a different one. The different IBA is IBA detectors. So IBA has a company that make detectors and also make a proton machine. So just not to confuse the two. They're the same company, but they focus on different things. They like to name their things by animals. So anytime you see a detector and it has an animal, it's coming from IBA. So the other one is called Lynx, Phoenix. This is called Stingray. So they have one, it's a 12 centimeter diameter. And pointing these out because in the next slide, you'll see why this is important. what their electrode spacing. You also need to characterize what the chamber, what it actually, the entrance window, because remember, you're doing an absolute measurement here in depth, so you have to know all these characteristics. Okay, so the reason those sizes are important. So here's a publication. I'll show some more data from mine, but just to kind of see that if you have detectors of different sizes, so this 0.4 cm detector, this is actually what we would call like a percent depth dose, or as the particle is going in, as your proton beam is going in, if you look at the central axis, so look at something that has maybe a 4 millimeter diameter just going all the way down, the beam you'd measure would look like this. So high here with a bright peak there. The bigger you get your detector, the more you're going to be measuring, and you're going to see that you're going to measure more like this. And these different sizes, you're going to get a difference here. The reason for that, and here's just a different showing, come out from here, just showing this aspect. Sorry. So what's happening is, remember earlier showed that as you're penetrating through water, the beam is getting bigger and bigger, right? It's scattering. And there's two types in general, and let's say in a first order approximation, there are two types of scatter. One is going to be coming from the electromagnetism, just kind of the standard thing that's going to be scattering. The second one is going to be coming from nuclear interactions. So you have a proton and actually interacting with another nucleus. And in that, you tend to get wide scatter. So if you're going to have that interaction, it's going to take like a big sharp turn, right? So the electromagnetism is just kind of a standard little scatter going, and then you get these big. So you have these two forces that are two type of scatters that's happening. Well, particularly that wide scatter, if your detector is not big enough, you're going to miss all these protons coming out. And if you're trying to do an absolute measurement, like say how many particles am I actually delivering here that's going into the patient, and how many am I going as a function of depth, you need to kind of account for all those. And as you saw, different size of the detectors, you're going to see some differences. And here's this is actually commissioning data. So from what I have, so this is for a low energy 71 MeV. So that means about 4 centimeter penetration. This is a medium energy 170, another energy, and then this is the high one 230. The difference here is going to be the difference between that bright peak chamber, the one that had an 8 cm diameter, and here the Monte Carlo simulation that has effectively an infinite chamber. And that's what you want, because you want to collect everything. So for low energy, the difference is very small. This is the difference between the two of them. Here you're talking about things that are going to be, 0.5%. So maybe, negligible. But when you come to here for these high energy, you can actually see the difference. You could have things up to, maybe 7% difference. That's something meaningful in knowing how this is taken into account. Again, the reason this is important is because when you put this into the treatment planning system, the first part is you don't know exactly what's coming out of the machine, right? So something's coming out. That something is going to be a spread in positions, kind of this spot size. It's also going to be a spread in energy. So synchrotrons can sometimes pull out really tight energy. So when I say a 70 MeV, there's going to be 70 MeV plus or minus like 0.5%, really tight. A cyclotron is going to be a little bit wider. We talked about that earlier because of energy degradation and such, but this might be a percent or two. So that's going to have different influence of how things, since you lose 1% per centimeter as you're going through all these different things. These are going to all look a little bit different depending on the machine you're using. And although they're going to be similar, it may be, 5% difference, 6% difference, or maybe 3% difference, depending on the exact characteristics of your system. So being able to do a proper Monte Carlo to say, this is what my system is actually going to look like, and then do the measurement to verify that and know where the differences are, be able to explain that. Because then your measurement or some data is what you put into that treatment planning system. in order to do calculations for patients. So all that to say that knowing these characteristics and why that chamber size is important. And then there's the bigger the chamber, it might seem better, but then there's also other things that may go wrong with larger chambers, meaning maybe the wall itself, you get now positional uncertainties. Yeah. So now this is going to be range measurements. What I'm showing here mainly, next slide talks about the detector we used to measure this. The reason I'm showing you this is when the vendor is going to say, I'm going to produce something that's going to come out and this is going to be the 70 MeV beam. And it's going to go through a lot of stuff through the nozzles. So it's going to be a little bit different than that. And that should correspond to a certain depth, 4 centimeters, let's say. It's actually not going to be precisely that. So what I'm showing here is basically if what the vendor said in their specifications were exactly true, we would have gotten this to all be 0. But there was variation, and you see how it is this wave pattern. And this is up to, even though it's, over here, 1/4 millimeter. So the difference between 2 different gantries, this was one gantry and the other, they were actually exactly opposite of each other. If you just took a standard average, you could have been off by maybe up to 1 millimeter. So saying this is just because all the characteristics, everything that comes through at the end, what really matters is the physical measurement you make. And that's why that has to be very precise. Because again, that's the thing that goes into the software that then does the calculation that's going to be used to treat the patient. So what do you use to actually do these measurements? So you talked about the chamber itself being like the Stingray Bright Peak chamber, and you buy those from a PTW or from an IBA, but then you need a water tank. And well, you can say, well, I have a water tank for my photon therapy, right? We in a photon therapy, you use a water tank because you measure there the PDDs, etc. And well, can I use that one? And the answer could be maybe, right? So kind of it depends. So the first thing is, okay, if you're going to do this surface measurement in photon therapy, as you know, as the beam goes through a patient, the exact surface doesn't matter too much. But now if you want to be really precise, as you're moving this from top to bottom, if you move it really slow, you're going to be okay. If you kind of move it fast, you may create little waves. If you ever looked at those, even though they're little waves, they're a few millimeters. And if you have a few millimeters and you're trying to do a measurement and being precise to less than a millimeter, you're going to get something different. So doing a measurement from top to bottom here is actually really hard to do it with the proton machine and get it exactly right. It can be done. The more preferable is to do something like this coming in through the side. Now through the side, it's not going to change. So you could do the side with the irregular photon water phantom. Problem is, it's a tank. So that has a certain thickness to it. And you could measure the thickness. You could then say, well, maybe it's the same thickness all the way through. Did they precisely do that? They probably didn't, because no one would care how thick it is all the way through. And then second, that's a plastic. Plastic is different than water, so it has a different characteristics. And so you have to characterize that beam, everything else. It becomes hard. So again, you can do it. So if you want to just use that water phantom, you can. It's just there's a lot more work that goes into it to make sure you're absolutely right to how you're going to treat the patient. So there are these ones that are used that actually have a window here, a really thin window that's very well characterized that you could do and use that. And then you could use the flip side to say, well, if need be, I could use this on my photon machine. That's okay. But the one using the photon machine, I would not necessarily use for the proton machine. So just thinking about this, and particularly if you're going to have a clinic where you're going to have your proton beam and your photon beam in the same building, like the one we're building. So we're going to have one water tank. I'm going to use it for photons and protons. Make sure it works for both. If you're in 2 different buildings, you don't want to necessarily move this tank from one building to the other one because the likelihood of something going wrong when you're moving it, because we want to be measuring these things moving very precise, something could go wrong. So how you're set up will really matter. Here's another one that's a little bit smaller if you're just doing the depth dose, that you could do this type of measurement. Again, so tools that are out there. And different companies, IBA makes one, PTW makes one. They're the ones that usually make most of those things. We talk a little bit about the absolute dose calibration. Now we did see earlier, I think was put out. I put there's over 130, 120, maybe 150 proton systems that exist throughout the world. But then if you think, oh, you got to throw away a chunk of those because they were double scattered, don't really count as the spot scanning anymore. And then depending on how you do your spot scanning, everything, I almost guarantee the system you're going to put in here, for example, the one room variant system, maybe that was, and the people in here probably know better, maybe that was like the third one room variant system. I don't know, it could have even been the first, I'm not sure. But that was the only one, or it was one of three, or something like that. Whatever you put in here may be the only one of that system, because it may be similar to the other one, but they made some improvement. They changed something. Hopefully they made it better, right? So you don't want the same system they put in 5 years ago. You want the system that's better. So you're probably going to have a unique system. So saying that, because though there is the IEA TRS 398 that talks about the absolute calibration, this is nowhere standardized as it would be for a photon, where there's 12,000 of these things out there and everything else, and everybody does it basically the same way, and it's been studied to death. There's not that many references out there. This gives away a method, but it's not really prescriptive purposefully, because every system's a little bit different in how you could treat versus when it was double scatter, spot scanning. Now, if you do spot scanning versus continuous scanning and all these there's so many variations in there that it's hard to kind of really come up. But they've given a guideline and it's something to actually go by. And those of you that have done what I'll call the TG51 or TG21 type calibration, this MQ is all your corrected readings. So your ion chamber correction factors, your electrometer correction factors, the polarity, everything else kind of all thrown in here. This is the one that has, this is the calibration coefficient at your quality at Q naught. So that's kind of familiar with photon therapy. Your Q naught is like cobalt. So you try to transfer everything cobalt. This KQ has what is going to be most of the physics in it. This is your beam quality factor. Oh, I don't have the laser on. I'm pointing at things and the laser is not on. I apologize. Okay. So I was pointing to things here. Didn't realize last time the laser was on, but this time it wasn't. Okay. MQ, the NDWK not, and the K, your KQ, your quality factor. So those that have done beam commissioning for photons, this nomenclature should be very familiar to you. The W here stands for water. But this K naught, the quality of the beam, how do you get that? Well, there's a guideline, and it says in there, it says you take whatever SOBP you're going to do, spread out bright peak. It doesn't tell you where to do it, and purposefully it doesn't tell you because every machine could be different. And it says you use your residual range. So wherever you're going to measure, you say how much more range do I have, and that comes from your residual range, and it gives a formula of how to measure that. And it says that's your beam quality. Now there is some physics behind this one, being that here you're using the end of range, so all the protons are going to have basically a similar energy. There's still some differences in there, but it gives you a guideline to be able to use. So that's how you go through to do absolute calibration. Still talking about absolute calibration a little bit. So you need some sort of reference field. When I do it with a Hitachi system, because whoever your manufacturer is, they have to do something to calibrate their monitor chambers in the head of their nozzle that's actually measuring the dose. And IBA does it different than Varian did it. It does different than Hitachi does it. So there's not a standard, right? Electa and Varian pretty much do it exactly the same way that they've been doing it for the last like 30 years or so. So pretty straightforward. Here, there's not really one. In a Hitachi system, we do a liter cube. That's kind of a standard thing where it's a 10 by 10 by 10, 10x, y, and 10 in depth. Now you have to pick a certain depth and get your residual range. And you can do this different depths and different sizes. So the guidance doesn't say to do it exactly a certain way. And again, purposefully, because things have been evolving from when it was written and knew that technology would be different. So they don't want to confine you to do it in a certain way. And also that's just a guideline. So it's not it's an international guideline. It's not a prescriptive regulation that this is how you must do it. As opposed to for APM in the US, and we have TG51, that is a best practices. And then the regulatory body usually says you have to follow the best practice. So even though it's coming from an association, the regulatory says you should do it that way. There's probably, well, you can see there's probably not a thing that says this is how the regulatory says this is how you calibrate the beam. You have to come up and say, this is how we will be calibrating for this particular machine, and this is why we're going to do it this way. And there's different ways to do it. You could do an SOBP or you could do it by a single point here. On the physics here, there's a reciprocity theorem that if you do a small beam with a big detector, the inverse of that is going to be a small detector, like a farmer chamber or something small, and a big beam, right? So you could get the same type of answer. The whole point is you want to make sure you're collecting everything of importance. So you could do it two different ways, doing absolute calibration. Most do it this way. In your treatment planning system, you're probably going to have to do these measurements because in this measurement, this is really how you're going to end up changing the number for protons, number of protons to a monitor unit value. So you're actually going to be counting protons when you do it this way. Again, there's no clear regulation or recipe exactly to follow. But in the ICRU, they do put out these for your KQ, this quality factor. So this is why on those ones, when you're doing the absolute calibration, you're going to use probably here, what I've used is the Marcus chamber. It probably doesn't show up, but the same Marcus chamber. And in these particular ranges, because you see, it doesn't change much as far as the beam quality. It's a fraction of a percent. Obviously, you don't want to use things different. You don't want to use detectors that have a large variation. Those are the ones that are red. Or do something that in this area that changes if you're slightly off. So in photon therapy, you usually do absolute calibration with a farmer chamber, a cylindrical chamber. Here we're going to be using a Marcus. And so that's different, and why you're doing it that way is different. The other thing that's trying to point out differences when you're doing these absolute calibrations to photons is when you create this spread out bright peak, if you're doing it in a spread out bright peak fashion, went quickly over how you make a spread out bright peak. It's essentially you put a bunch of bright peaks together to get something nice and flat. Well, you don't have an infinite number of bright peaks you're going to use. There's always going to be a finite number, and they're going to be separated by so far. So you're never going to get something perfectly flat. And I'll show actual measurements in a bit. This is a cartoon, but I'll show measurements in a bit. So now you're going to do an absolute calibration. Well, where are you measuring? Are you measuring right here at a peak, or are you here at a trough? Where are you? So sometimes you have to really do a fine measurement kind of here to go through and make sure you're kind of in the middle, or you do one at different parts and then take averages. Again, something different than you're used to doing for photon therapy. And if you just blindly kind of go, put this out there to go, that variation could be, 1.5%. So then you're always going to be 1.5% off. And that might seem small, but when you really start to think you're percent here, percent there, everything else, then you add up maybe, you're a few percent off. And it's already hard enough making sure you're delivering the exact right thing to the patient with the CTV, PTV, everything else. When you could be really precise in the physics, you should be really precise so that any uncertainty is then in the actual patient delivery and anatomical changes are happening. And it's not something because your physics was off by 2% or such. Even though in general, when we do regulatory things, there's usually plus minus 3%. You should be as precise as possible. But this is different than photon therapy. Photons, you go to 10 cm depth, that's your reference depth. Everything's been well characterized. It's going to be nice and flat and uniform, not necessarily in proton therapy. Right, so the ion chamber that you're actually going to use, again, so we're talking about absolute calibration. This is how you treat the patient, right? This is counting your protons to change them into the actual dose, those joules per kilogram. So parallel plate, that's the commonly used in IMPT or proton therapy. It has usually a better defined effective point of measurement. This might be a little bit in the weeds for those that are into the medical physics, but one of the things we want to talk about is the detectors, so we got to go into them a little bit. And also usually has a better collection efficiency for high dose rate. When we say high dose rate, it's not necessarily when you're talking about the dose rate, when you're thinking about treating a patient dose rate. This is the dose rate, that instantaneous thing that you're seeing. And it's the next slide. So I'll talk about that in the next slide. Cylindrical chambers, like your farmer chambers and such, they're usually, you could get that from an accredited body to give you an absolute calibration. You could do that for the Marcus chamber as well, but usually they do that for farmer chambers. And in general, these cylindrical chambers have, over its lifetime, a better characteristics. They fly a little bit better. But again, photon therapy, you generally use these cylindrical type, farmer type chambers. In particle therapy, you generally use these parallel plate chambers like the Marcus chamber. Talk again about, fractions of percent. But it's, again, I think these are always important, particularly when you talk about proton therapy, because not only do you have the patient variation, then you still have a little bit of the radiobiologically, the RBE slight uncertainty. And, again, we want to make sure the physics is right, because we can get the physics right and then leave the uncertainty to the radiation biology and such. So you have to decide when you, sorry, it says TRD, oops, typo. Yeah, I got to change that. TRS 398. It says, it makes a statement. Proton synchrotron beams of long duration and low pulse repetition frequency may be considered as continuous. So this is a statement that then you kind of look at that, then you have to ask a couple questions. What does long pulse duration mean and low pulse repetition? These are just vague words. Relative to what? Long relative to what? Low repetition relative to what, right? So these kind of, and this comes in when you're doing this calibration, you have something called continuous. Now, I'm not talking about how you're treating the patient, but another thing, you have a continuous radiation, pulse radiation, or mixture. And depending how you calibrate, and part of these things you have to take into part of your quality factor when you're taking into account changing for that MRAW. There's differences, and this is kind of vague. I, again, put out the synchrotron. But when you actually do measurements and do things different ways, you can see that the statement that's made there is not necessarily right. And if you just follow that, again, you might be 0.5% off. Again, 0.5%, you say don't really worry about it. But again, there was half here, half there, a quarter there. It kind of adds up. So again, it's just for the particular machine that you're going to be installing. And it's probably whatever it was, the design was yesterday. Hopefully what they're going to put in here isn't the exact same that they did 3 or 4 years ago. They've made improvements. They made it better. So it may be unique or fairly unique. So how does it fall into this? Important to kind of understand that. A lot of people for proton therapy want to use film to be able to do a lot of measurements. Film is very good. One, it's cheap, so that's great. particularly graphicomic, you have film, you don't need a processor, you just need the scanner, and so that's pretty good. Problem is film has this property that it'll do this quenching. So it's a physical property. All detectors have these kind of things, limitations. So if you're doing film and you're doing whatever kind of measurement you're doing, whether it's an in-air measurement of the profile or different things, you may quench depending, and it has a different property depending on what LET you're going to have. So this comes from a publication that we did just to kind of show that there was this characteristics. There was a clinic that tried to do a calibration based on a film and do IDD and didn't properly correct for this and were a few percent off, and it was enough that it was able to be picked up. So something else, another recommendation: once you do everything, you calibrate this, and you invite your friends from Singapore, because they're not that far away, and have them come with a couple detectors of their own, totally separate, come in and do some measurements just as a sanity check to make sure something wasn't just, kind of off. So it's good to get totally independent, someone else doing it with their equipment, because something could have been wrong with the equipment used or whatever it is. And before you actually treat a patient and give radiation to them and do that secondary check. Important, pick up things that are like, oh, oops, did something quite not exactly right. Anyway, so just knowing that your detector, your film, anything else have some properties that may not be suitable with proton therapy. Another thing that's very important, we talked about all the IDD measurements. Now, another important characteristic is, what does your spot look like? What does that spot profile look like? So here's one, just talked about film. Here's one measured with film. So measured, this is in air. So very low, relatively low LET, so not a fear of quenching. But you get here, and the red is the diode, the blue is the film. So okay, that looks fine. But then that looked like just a regular Gaussian. And now we're in log scale, and this red is a Gaussian fit to the film measurements, and by the way, to the diode measurements, a Gaussian fit. You see, when you go in this log scale and you go down 2 orders of magnitude, you get these wide tails. So here did a 2 film measurement, 2 different type of calibrations so that we could get really low and really high doses. The film doesn't have enough dynamic range to do both. The reason this is important is because you have to characterize these tails. And again, whatever system you put in, this thing down the 2% and below is going to be very unique to your system. Of course, your spot shape, your sigma and stuff is going to be unique, but depending what it goes through, what kind of thing it hits during the nozzle, how the monitor chambers are made, how the spot position monitors are made, all these different things add to these wide tails. And you think, oh, these wide tails, that's no big deal. Again, 1%. But when you're doing spot scanning, you got to remember the fill. When you're treating with this, you're treating with a bunch of spots. And this is a very simplified case where you're going to have your isocenter here. Well, all these spots are contributing in their wide tails to the center. And if you didn't properly characterize those wide tails, you could be off if you said, if it was just a perfect Gaussian, it looks like this. But here, depending on how many of these spots are contributing, it could be very different here, up to 10%. Again, depending how you calibrate and what you're looking at. Putting this one in more, because tomorrow's talk, you see why a good algorithm is required. So when we talk about treatment planning systems, I'll talk about that. But again, characterizing that beam, and the beam that you're going to commission here is going to be different than anybody else's. Getting those tails proper, understanding them is important. So again, the tool you use, whether you use film and knowing how your dynamic range to be able to characterize it, use a scintillator or different things. Okay. Let's move on a little bit to some different measurements. So we talked about the water phantom and doing that absolute calibration. It's also important to, on a regular basis, and you have to determine for yourself how often regular means to measure these integrated depth dose. Something could happen to the machine over time. The other thing is also anytime the vendor has to come in and fix something, you have to check these things. And this is one just out of experience. Something the dose monitor was acting a little bit funny. So, okay, so fine, good. Had the vendor come in to go and, correct it. They did what they needed to do. And all was good. They did their beam test, everything else, everything looked good. But then, so, they wanted to be mom. And I said, wait, we got to do a few things. You actually went in and took all these things off and put them back on. I want to check and make sure that things happen. So I wanted to check the beam profiles and the depth doses. On that one, I did a more simplified measurement than this. But the key on that one is the vendor forgot to put something back in. And it wasn't a safety thing. It wasn't anything else. It was just a protective film. So when everything's there, then it's just a film that kind of protects in case something falls so it doesn't fall into the nozzle. They just actually forgot to put that one piece back on. But that has a certain thickness. And if they left it off and you treat it, all the depth doses are going to be off by that thickness. And that's why you have to go in and know what they did, what they took off, put back, and do a measurement that's meaningful so you could check. So I checked spot shape and size to make sure something scatter-wise didn't change, and checked the depth doses, just a few of them to make sure something didn't change. And that aspect that it picked up, hey, there was something different. So this is the IBA, the giraffe. This one has a bunch of multi-layer ion chambers in here. You put a spot through there, and then you can measure that spot profile. It's not a true integrated depth dose because it's not in the water and it doesn't measure everything, but you could get a good measurement and quality assurance to make sure everything is acting right. They first came out with this one was called the Zebra. This one is a lot more complicated device, but it's not as useful. This one's actually simpler and more useful and actually cheaper, more useful for spot scanning systems. This was very useful for double scatter. But these have small chambers, and if you're doing SOBPs and just checking things, that's important, i.e. kind of more double scatter, but this is more important for spot scanning. And luckily it's cheaper also. But these are detectors out there that you can buy that help you ensure your quality assurance, your quality control of the machine. So you don't have to bring out that big water tank all the time. And anybody has used those, you don't want to use them except for like once a year. Scintillators. So there's a lot of detectors now that are based on scintillator technology. Some more coming out. Maybe by the time you're ready to go live, there'll be some more interesting aspects here. But these, you're able to do some very interesting measurements. But again, you need to know its limitations. So this is measurements in proton. There is LET quenching, kind of like photons, but you could correct for them. We're just pointing this out because then we actually took one of these devices and went and did it in a carbon center. And you can see that there's a lot of quenching in the carbon center. So again, things that we could go and correct, but just knowing that device, how it's used and where it can actually be used for. Other things that you want to test. So this is a 2D chamber array, so flatness and symmetry. This is something that in photon therapy you're really used to checking. It might not make as much sense to check flatness and symmetry, but this is a good way to, if you have a standard field that you can kind of put in there to ensure that the scanning and everything else is still working properly, that you are able to actually scan the way you were scanning before, particularly if you're doing a continuous scanning and stuff that actually maintains. Other things that you're going to be using a detector for, this is the logo system. So remember, now we have a beam, one spot going down the central axis, and you want to check your gantry rotation. You want to check mechanical isocenter versus radiation isocenter in photons, where you're doing this Winston-Lutz type of check. Similar, but you have a different radiation mechanism and you have a single spot. So different ways you could check that. So this is one method to go ahead and check that. Here's some measurement results. Just kind of showing. So then you could check your radiation and mechanical isocenter as the gantry is rotating, and you could do this also with your patient positioner as it moves. This is a nice daily QA phantom that you could just kind of set up and do some sphinx. So uh, it can test a lot of things really quickly, something good on a day-to-day basis to just check properties, some basic properties of the machine. Particularly for proton machine, the vendors are always doing things at night. And we'll talk about that later when we talk about access hours and such. But they do a lot of beam tuning. And then they do some beam tuning, and then they have their quality control procedure they do before they hand it over at 6 a.m. or 7 a.m., wherever you take it in the morning. But they did tune the beam at night. So it's always good to have, just like with photons, a daily check to check some parameters to make sure they didn't overtune or mistune or do something weird. Particularly if you are going to have a strong research component. We did a lot of research on the weekend, but also overnight. And sometimes you want the research component to be done during in not a clinical mode, because you're doing something different. You're doing research. You're not using clinical mode. So making sure it's back working properly. It's the research team should do that. But as a clinical team, you should check. So to have a daily QA set up, they could check some key parameters. And it's fairly straightforward. These are just some different things that go in that you can check. This is a water tank that has this matrix. Later, I think on another talk, I talk about patient-specific QA and being able to do log-based and such. A lot of people do these measurements. These are very detailed measurements, and those that have went to, and hopefully the regulatory body here, we can have good discussions so they don't make you do these kind of things, because they're not really useful in general, but they're really time-consuming, and people spend hours doing these. And one, they're not very meaningful, but they feel either on some, and some in Europe, their regulatory body has told them they have to do this because they don't really understand it, unfortunately. So they spend a lot of time doing these measurements, which means they're not treating patients at that time. So this is a device that exists. I never use it. But again, hopefully your regulatory body won't make you do these kind of things. Your machine has to be capable of gating. Gating means turning the beam on and off, like on a respiratory signal or any type of signal that you want to be able to say the tumor is in position, out of position. It could be as simple as, the trace, and we talked about getting a little bit before patients breathing, or it could be the therapist just holding the button saying beam on, beam off, kind of watching whatever signal. Maybe you're doing fluoroscopy, whatever it is. But you have to be able to test at the gate that the system can turn on and off the way it says it's supposed to do that. Usually do that with an oscilloscope, just be able to see it turn on and off. You can do this different ways, but it's an important thing to measure. A little bit now, throw on aside, because another thing is that's different for proton therapy is for your CT scanner. You have to be able to, you aren't changing to electron density, you're changing to relative stopping power. So the proton center here does dual energy, so it's great. The dual energy, as long as it's a proper dual energy, well separated, will give you a good estimation of the relative stopping powers. If you don't, if you have a single energy, you have to do some commissioning to be able to test these. And again, this is set up for a photon therapy. So these are set up to measure electron densities, not relative stopping power. So you have to go through a procedure to try to convert that. And there is uncertainty in that, unfortunately, more than we would like. But there's ways to reduce that. And one good way is use a dual energy, a proper dual energy using property. You could reduce some of those range uncertainties. So some nomenclature, we usually all do all these in water, but you may hear people say this, so I want to put it out. This comes a lot from the double scatter method, but the modulation, when somebody says there's a certain modulation, they usually mean the distal 90, from wherever your peak is, the distal 90% to the proximal 90, would say that's their modulation. This nomenclature could someone say, oh, do a field, a certain modulation. And the range also goes, use a lot to use the distal 90, the 90% of the peak. I usually, when I'm doing my calibration in mine, I use the distal 80 as the range. Uh, there's more of a nuclear physics why I use that one, but people use different, so it's good to understand when people are talking about range. And your vendor and you, are you talking about the 90%? Are you talking about the peak? Are you talking about the 80%? What do you mean by range? There's not a true definition in the vocabulary when people say range. Uh, so we talked about mechanical, the radiation imaging. You have to do end-to-end test, the safety interlocks, and also the integration with your hospital systems. These are important, again, because it's the acceptance test. What tools are you going to use? They're sometimes different than you use in photon therapy. So just to really quickly, since this is more mechanical side, these are things you have to test. The patient position is usually more complex than a photon one. Your gantry rotation, you saw how big these things are, so they do have sag. And an important thing to remember is not only is there a mechanical sag, like physically when the gantry is rotating, but those magnets themselves, when you're rotating, they slightly shift. And when they shift, the beam optics change. When the beam optics change, the spot characteristics change. So again, whatever you measure at one angle is not necessarily what you'll measure at a different angle. So it's important to test the different angles radiation-wise as well. Uh, the gantry isocenter mechanical. Again, this is one of the things, and it's probably better doing it this way. I will, as a clinic, you should not buy this thing, right? Because you're going to use it one time during acceptance and technical commissioning. And then you're going to do other tests, but this is the high precision test. So this is something the vendor should have, and you use their tool when you're doing it. On the flip side, the vendor is probably not going to bring their water tank to do the measurements. So they'll probably use your water tank to do some of those measurements. So, just discuss with the vendor. But anyways, you got to test the mechanical isocenter. And, again, you have to have specifications. And it does have, and this is just mechanical now, of motion of when it's going around. You have to have where you want it, and it has to be below a certain, and it's not symmetric. So again, now it's moving slightly non-symmetric. And again, this could be a millimeter. And again, when we talk about things adding up, that's just the gantry. What about the couch itself? So something else you generally don't worry about too much about in proton therapy is, the couch. But in protons, a lot of times we do a fair number of couch kicks, and we might pitch the patient a little bit, but it's more of a robot than a standard couch. And you usually have a calibration volume of where within that area are you very precise, that the couch can actually move very precise. So knowing how big and measuring those and measuring it with weight on, with weight off, all these different kinds of things. So the various weight distributions. And the vendor may want a very small calibration volume because it's easier for them. But if it's very small, then what happens when you're outside of that, particularly doing these cranial spinals, these long treatment fields? So 100 centimeters, that's a meter. That's a pretty good size. But I've seen some where they try to say their calibration volume is actually much smaller, like 50 by 50 by 50, right? That's just too crazy small. Same thing with the couch. So with the gantry and couch combined, now you got to move these two things together. You usually do that for Linux when you're doing the stereotactic. So when you're doing stereotactic, you'll measure couch and gantry together. Otherwise, you generally measure the gantry alone. Again, these are standard measures. These are mechanical. But then when you're now talking about the overall, when you have the beam also coming through. So in a different test, you measure, does the beam actually go where it's supposed to, like 20 by 20 or but in the corners? But now how is the beam coming out relative to a gantry rotation, relative to the couch? So all these things put together. And that's, again, so important because you got the mechanical, but as the gantry rotates, those magnets slightly shift, the phase changes. So the beam that comes out at 0 degrees is different than when it comes out at 90 in all the other angles. And some vendors will tune a few gantry angles and interpolate between them. Some will only measure like 2 or 3 and interpolate, and then you get the wide variation. Won't spend too much time on this, but the image guidance is very important, obviously, to do that. Everything now is cone beam based. They're doing a very high precision. So if are they mounted on the gantry? Are they mounted separate from the gantry? All these things that go into consideration. So if they're mounted on the gantry, do they sag? If they're coming out, do they have different things? So, for example, this is an oven just for the sake of argument. Hitachi has machines where they do different. Some are mounted here, some come out from the back. So they're always different, and they all have their different limitations. So this is just a phantom, a Medcom phantom put out there to help test all these different things. And then the final is the true isocenter when you get all the things placed together, mechanical, radiation. So I was saying at different gantry angles, the radiation slightly changes. Some vendors want to correct that by what they'll try to correct it with the couch. There's that kind of correction, or you can correct it either with the scanning magnets or steering magnets. So knowing how your vendor is actually going to correct that matters, because how you're going to actually then prove that it's actually going to the right place. And if something changes, did they actually still using the same mechanism, and is it reproducible? So different ways to do radiation isocenter, different ways for the vendor to do radiation isocenter corrections. And they each have their pluses and minuses. I like it what they do with the steering magnets as opposed to moving the couch. Yeah, again, when you're doing imaging, you can use the radiographic here just to do different tests. I think some of you will be familiar with this because you probably do this when you're doing cone beam CT or proton measurements. If your system has fluoro, you got to be able to do the fluoro tests. So again, these are the standard ones. Won't spend too much time since they're not proton specific, but they are a little bit different than your standard photon machine, mainly because whatever cone beam system you're putting in, that system is probably the only one of its kind, or maybe it's the second one, right? Whereas a Varian True Beam, we saw that, they had the Varian True Beam and Ethos earlier. Well, there's 10,000 of those that exist. So it's been well tested. The one you're put in is probably the first or second one that vendor or that system. So there's going to be all kinds of things that are going to be a little bit odd, and like, why isn't this as good as it is? Or how can you actually improve it so that you can have better patient treatments? So all those various items, the standard, this is the same phantom that we use on the proton. So no need to go into it in too much detail. Just the different tests you're going to do. This one I want to point out is a phantom that I think would be a device that would be helpful is an anthropomorphic phantom. Again, the reason if you're doing this with a Varian True Beam, let's say, again, there's 1,000 of them that exist. How it performs, or you could go somewhere else and see how that one performed. The registration system that whatever company you're going with, they have to write software code to do the registration. And how well did they write that code? How well does it perform for different anatomical sites? And sometimes, and this has happened before, they write the code very, very well, and it works really good on the phantom they used and was horrible with anything else. So you can do that. You can over process your thing and make it work really well for one particular thing and not something different. And as you know, if you're going to treat from basically head to toe, there's going to be all kinds of different anatomical sites you need to be able to test. So having a good phantom that you could test these different things is important. Again, something you won't normally worry about with photons, but again, if it's a proton system that there's only maybe 2 of them that exist, 3 of them, and their IGRT is relatively new, it's important. Yeah, so there's different of those phantoms. There's pixie phantoms, different things, rigid bodies to be able to test, and make sure it picks things up. You can actually move them and do these things. knowing how that proton nozzle is very large, just how you've seen them. And if your imagers are attached to the nozzle, there's going to be times when you're going to have obstruction. So you have to understand how that obstruction or where the obstruction is. And if you're going to be doing a cone beam and you're going to be slightly off center, are you going to actually be able to see anything? That's part of the things you write during your acceptance test and your acceptance test procedures, and have the conversation with the vendor. Because the worst thing is you get all these things, you test everything nice at isocenter, but then you're doing a breast treatment that you're slightly off and you had to shift, and now you can't see anything because the imagers are being obstructed. And I'll just say, because of registration time, again, you can have a very good registration system, but if it takes a minute for it to do a good registration, it's not very good because now you've wasted all that time. So having all those, these are things that, again, that you might not normally test in a traditional photon system just because there's a lot of them, but in your proton system, you may want to be able to look at. So with that one, I'll take any questions on, well, any questions that you have on any subject to be fine. Thank you. Any questions?
I have one question, please. I have an experience for the proton dosimetry at the Chulalongkorn Hospital last year, and we use the loose ionization chamber. It's a plane parallel to measure the proton dosimetry, and we use the calibration factor from the in a cobalt 60. And for the TIS 398 new version, is recommend to use the cross calibration rather than the cobalt 60 because of the P-wall.
Yeah.
So what do you think about the P-wall is P-wall effect a large difference between the cross calibration and calibration in the cobalt 60?
Yeah, so that's, again, that's what we're talking about. I think the P wall is probably like 0.25% to maybe 0.5, and taking those into account is important. So I do think the new version has a little bit better mechanism. So instead of doing a cross calibration where you would say, here's my, with the Ross one versus a Marcus chamber, anything, basically kind of the same mechanism, right? So here, do you send, so for your reference chamber, do you have a calibration lab that's here in Thailand that you send it to, or
in Thailand, we have a cobalt 60 to calibrate the parallel plate and also the cylindrical chamber as well. So we can do for the both techniques, for the cross calibration and for the calibration in cobalt 60.
Yeah.
So, but for the convenient for us to measure the proton dosimetry, so we use the loose to calibrate it in the cobalt 60, and then we correct the KQ by using the table in the TIS 398.
Yeah.
Yes.
Yeah, so that's similar to what we did. We didn't, so we used the Marcus chamber, but we didn't send the Marcus chamber out. We cross calibrated it with the Farmer chamber. So again, which is 2 cobalt 60. I think on either mechanism, I think it's fine as long as you know where that limitation is, right? So once you are doing that correction, you know where your potential error lies. So P wall is, particularly for the parallel plate chamber, well, for the Marcus chamber isn't that much of an issue, as opposed to, because if you cross calibrate with the Farmer chamber that has the P wall correction, you have that uncertainty kind of built in. So we knew when we did that we had that uncertainty that, okay, the P wall there isn't the same that the P wall that we're going to have when we do this cross calibration. but it was, relatively small. So we said we were okay with that aspect. But again, just knowing where those come from is important. Yeah. So sending off and, when you get and the other question is, when you send it off, do you do them both calibrated together, the electrometer and the chamber, or do you do those as separate things? Because that's another one of the kind of questions, not really about when you're doing your absolute calibration, is then knowing that the two things were done together or they were done separately, because that also adds a little bit of uncertainty. When small piece, but a little bit of uncertainty there. So I know here, do you send them as a unit, electrometer and chamber as one unit, or do you send them as separate things? So I'm usually we send them as separate, and you have the two different correction factors together. But
ไม่ต้อง cross IC หรอ
like, yeah, so I see the Ross chamber and the Marcus chamber are very similar when they have here. So as far as the when you have a particular residual range and the quality factor, so both of them have that similarity. I was trying to see on the table, but I couldn't see it on the table.
So
Yeah, but on these correction factors here, all the different correction factors that go into making this up,
So yeah, in your hospital, you do cross calibration. Mean you measure with IC and then you cross from IC to parallel.
Yeah.
In the proton beam, right?
Yeah.
Yeah, this I think is normally. And what is the key energy you use for do the cross calibration?
Yeah. So you do that this so for our system, since we did the calibration, we did from 10 cm to 20 cm was the cube, 10 cm to 20 in the middle. So then the residual range was that 5 cm from the middle to there. So it'd be similar to us here. So residual range there would have been the 5 cm. So that's where we measured, and then did the scan back and forth a little bit because there is the ripple, and trying to say and that the issue with the farmer type chamber is then exactly where the effective point of measurement is. So I had to get that average and put it out. The other way is just to cross calibrate in the photon, right? Just to make sure that they are the same. So kind of do both methods, see you get basically the same cross calibration factor to say, okay, now it's done. Since we didn't send off the Marcus chamber itself to get to the accredited lab.
So but right now the newest version of T9A that recommend to cross calibrate at the plateau region, but how much difference you do the cross calibration at the SOBP, right?
Yeah, so you could do it on either one. As again, the plus of doing it in the plateau, the entrance at X depth, whatever you decide to do, is it's usually flat, but if you look at it, it's not necessarily flat. There's a slight slope to it, right? So then you have your slight position variation depending exactly where you are. Rather, if you did, depending how flat your SOBP is and how those ripples are, then you can get a little bit flatter, more symmetric there than here if you have a slight positional uncertainty. So that's kind of, so there's nothing like kind of for free. Right? So if you put it here, how flat are you kind of coming in? If you put it here, what's your ripple? So it's like, so you kind of just you can do a little bit of both and kind of check and make sure that you're, if you do it the same way, you should get the same answer. So if you get basically the same answer to within 0.5%, then you didn't go too far wrong. So kind of the same thing of, measure twice and then cut one time. So kind of do it two different ways and say, I got the same answer. I didn't do something wrong, and then go forward.
Maybe the last question for me, how do you get the correction factor for the quenching effect? You compare with IC and or you do the
like for film?
no, yeah, maybe film or scintillation detector or
Yeah. So so my background is nuclear and accelerated physics. What I did a lot of there, I did a lot of computation, did a lot of Monte Carlo simulations. So my crutch, or the thing I always fall back, is the Monte Carlo simulations. So I usually use that as my benchmark, as kind of my ground truth, and then do measurements with good somebody you trust, like Marcus Chamber or something like that. And then I have my ground truth and know the Monte Carlo simulations are accurate. And then when I do something like a scintillator or a film, the first thing is, the assumption is that it's going to have some issue, either a quenching issue, or if it's a new type of detector, maybe it has a pile up or too much of a dead time, right? So if it has a certain readout. So I always assume something's going to go wrong and take the measurements. And when I see those variations, then go in. So on the film, we actually had the Monte Carlo, had seen before that there was this effect, this quenching effect. So then just did the study of going very detailed to measure the different points to kind of bring out what was, because it wasn't exactly directly related to LET. It's a little bit more, but you could say that on an average and do the correction. Yeah, but every detector has an issue, right? There's not a magic detector that kind of solves all your problems. No.
Okay, thank you มีคำถามจากท่านอื่นไหมคะ
I wonder about the spot size.
Mhm.
Usually when we teach the proton, we have to teach some gantry is through the couch. And do we need to measurement the spot size that pass through the couch?
Yeah, so I'll take one step back. So anytime so in your treatment planning system, so part of it is, how does the treatment planning system work? So in the treatment planning system, most treatment planning systems, because everybody could be a little bit different, there's an external structure, right? And the external structure is where the treatment planning system starts the calculation. If you're including the couch in your external, and you've characterized the couch. So the way it shows up on if your couch in the treatment machine is either the same as when you simulate, or you have like some treatment planning system lets you insert a couch and you put it in the property and you've characterized it well. And if it's in your external, then you don't have to really look at that and say, take into account and say, how did the couch change my spot size? Because it's in the calculation. And most couches now are like carbon fibers, so they have very minor impact. It's more not necessarily spot size, it's more of a robustness issue. The robustness issue is, if you're going straight through the couch it's not an issue. If you're going through the edge, where it's a little bit thicker and more, the patient is never exactly in the exact same position on the couch, right? They're a little bit there, and you set up the patient, you get the patient right position. Now, if the couch you thought was in the beam, at simulation, you were going to go through and you're going to go through it, but now they're lined up and you're not going through it. Now that could be, depending on that couch thickness, up to a millimeter difference. So that really comes more on the robustness aspect. So if you're doing so not to say that you have to measure, because you can see it's carbon fiber, I know, and you're going to take it into account during the calculation. But during your robustness, either evaluation or robustness optimization, you should make sure, if you are, like I would just always tell our treatment planning, just to give at least a 2 cm. If your beam's going through, give 2. If you can't, then know that you're going to have a little bit more uncertainty there and make sure it's taken into account. Because when you do the robustness, it usually takes into account the patient position uncertainty. And again, depending how it's set up, that may or may not take into account. Patient is right, but now the couch isn't there, right? It can't take that into account that this is right and this is wrong. So you kind of look at that, and I usually do that under robustness evaluation to say, now what if this part was a millimeter different? But if you do 3 millimeter percent, 3 millimeter range, and I mean 3% range or 4% range, and 2 or 3 millimeters, then in that robustness, it's usually taken already into account. But it is something important to look at because some do have like thick areas, like for stiffness, and you need to avoid those during treatment planning.
Thank you.
Yeah.
Any question? Any question on the floor?
So if you have no question, actually we have no closing ceremony. So thank you very much, Professor Chris,
Thank you very much.
coming to OAP to discuss about the proton therapy. This is quite new for us for the proton therapy. Hopefully for the next future, we have like a cooperation together again. So thank you very much.
Thank you. Have a good night. And we have more fun education tomorrow too.